Right, so this is going to be a talk about universal algebra, preparing a talk about other universal algebra stuff, about ideals in universal algebra. And, um, right, so what is universal algebra about? Usually in regular algebra that you study at university, you study just specific instances of algebraic structures like fields or groups or monoids or maybe quasi-groups and things like that. And universal algebra, kind of similar to more um, large picture view, like in category theory, you view just the concept of algebraic structure kind of as one thing and consider algebraic structures in general. And then your theorems are about all algebraic structures or all algebraic structures satisfying certain properties. Um, so this view is pretty model theoretic. So the talk will start off with some model theory. Wait, let me see. No, I have to. It's kind of dumb because I have to stop talking in order to move the slides, but I guess it's going to be fine. So we'll start off with some model theory. This is just the standard model theory background. This is going to be necessary to understand more universal algebra. Well, it's language structures and algebraic structures, and last part of model theory here is rather universal algebra already, but yeah. Then we'll talk just about general things in universal algebra. So morphisms, substructures, products, congruences, quotients. I mean, those are just rough headers. There's more there. Then varieties, and varieties doesn't refer to the same thing. Varieties doesn't algebraic geometry. A variety in universal algebra is sort of something like a category of algebraic structures. I mean, you kind of can think of it this way. Those varieties are the main thing you study in universal algebra. And then we'll just look at some toy theorems that like are in the subjects that are good to know. So let's start off with languages. Oh, yeah, here we go. So what's a language? Well, a language is going to be the sort of background symbols and basically symbols we need in order to do maths. So a language is going to consist formally, as I said, so let me say this now at the beginning of the talk, that everything I'm doing here is going to be doable in set theory, even if you're talking about like fundamental things like models, structures, and like things like that. Everything here is in the context of set theory, just because it makes stuff viewing things easier. I talked about this. I talked about this with Nikolai earlier a little bit in the Discord. But yeah. Um, so yeah. I also use classes, so it's not just sets and ZFC set theory. We can use NBG or something like that. It doesn't really matter for that matter. So a language consists of symbols, specifically operation symbols and relation symbols. And sometimes you view constant symbols, which are in this view a kind of operation symbols, also separately. But here in the way that I've typed things up and the conventions that the book I referenced follows, constant symbols are also operation symbols, namely operation symbols of arity 0, and the arity of a relation or operation symbol is just a natural number that is arbitrarily associated to it in a given language. Also, one thing to mention that people usually don't mention is strictly in a language we also need an alphabet, which is going to be the set whose elements are going to be called variables. So this, usually when you speak of variables, here we formalize that by thinking of variables as just some elements of a set. And so usually it's completely implicit, and this you also take. I wouldn't always write some alphabet. It's just we have some implicit alphabet whose elements we call variables. This is something we need. Um, and then we have just offset operation symbols, relation symbols, each of an arity. Right. And now when we have a language, you can define something called terms, which are just the thing that you know from usual maths. We have for any variable x a string x a term, and if you have some operation symbol and some terms, we can kind of apply the operation symbol to those terms, and then as a string, this is going to be a new term. So here's maybe an example of terms. Here you have the language having a binary operation symbol multiplication and constant symbol 1. Then we have these two strings be terms. And strictly speaking here, there should be parentheses, if you note. But very often parentheses are implicit. Like people don't write an infinitude of parentheses just because that's more convenient. When everything is clear, it doesn't really matter. So 1 times x should be bracket or parentheses 1 times x parentheses close, and the same thing here. But yeah, so terms are just obvious things. Now we can consider them our arbitrary languages. Um, Now we have that, and we're going to want to express statements in a language, and for that we need to first introduce something which is called a formulae, or a formula, and the plural formulae. And this is also defined recursively. First of all, for any terms over the language L, we have this following term that they quote unquote equal a formula. For a relation of arity M and M terms, we have this thing, a formula. So, and negations and conjunctions of formulae, and we can also now speak of disjunctions and implications just by viewing them as like another way of writing these, just these formulae that not phi and not psi, just going to be standing for phi or psi, and the same thing with implication. And now finally, it's called first order logic because we also have quantification, now it be zero order logic. Formulae in which, so we have some formula and then there's some variable symbols in it. If in this formula nowhere this existential quantifier symbol occurs, we call the variables which occur in it just the free variables of the formula. If it does occur, then the variables which it occurs before are called bounded and are no longer considered free variables of the formula. And we can formulate to say recursively that if you have a formula phi with free variables, with a free variable x, then the existent x such that phi, written as such, is also a formula, but now it doesn't have x as a free variable anymore. And then we can do the same thing with quantification, except we now define quantification through this existential, the universal quantification through this existential quantifier as following the negation of the existence of an x which satisfies the negation of phi. And this is not fully constructive. I mean, yeah, I'm doing constructive mathematics here, so it doesn't matter, but just if somebody's going to be watching the recording, maybe Nikolai will watch it and get angry that it's not constructive. Or just generally, this is not constructive, but this can be fixed if we consider universal quantification and things just separately as more things to add to the way we construct formulae. So now we've defined what formulae are, and now we can speak of statements of our language, and those are going to be formulae without free variables. So for example, if in the example from before, 1 times x, we make that into formulae by saying 1 times x equals x. This is going to be, by the first point here, a formula, a string. And then if we quantify, so it has one free variable x, and if we quantify it for all x, 1 times x equals x, now this is a sentence because it has no free variables anymore. By quantifying x, we removed it from the free variables. And now the sentence can be thought of as a statement, and it's going to be more formalized now with so-called structures that we can interpret these things. And free variables, the set of all free variables of formula usually denoted fv of phi, for phi the formula. And also one important point, a set whose elements are sentences over some language is called a theory over that language, an axiomatic system over that language. So this is going to allow us to formalize things like piano arithmetic, that's an axiomatic theory. What that precisely is going to mean is that it's a set of sentences. So this kind of formalize it in model theory and set theory. All right, so now let's fix language. And so far, this was all very like hypothetical in that we just consider these terms as something that doesn't really exist. We just kind of make them up as strings. But we can also think about it, how we can interpret in usual maths and set theory means structures. And so if you have a language, we can speak of an L structure if the language is L, and it's going to consist of a set, and for every relation symbol, a relation of the same arity, every operation symbol, an operation of the same arity. And in particular for constants, we're going to have nullary operations, and that's basically the same thing as elements. Well, strictly speaking, if you haven't seen this before, a nullary operation, so first of all, just in case somebody listening isn't familiar, what is the relation? An n- ary relation on a set is just a subset of this set to the n, it's a Cartesian product. And now we can say that some element of the Cartesian product x to the n for x to z is satisfied by the relation if it's an element of the relation. And n-ary operations are just functions from m to the n to m for m, say the set which is done. And now a nullary operation on a set M is a function m to the 0 to m. Well, what's m to the 0? Well, strictly speaking, that's a singleton whose only element is the empty set. And in fact, it's going to be functions from a set which has one element to the set M. So it's basically the same thing as picking out an element. This is just a formality, but basically constants now are basically the same thing as elements of M. And these things that we get, Fm, Rm, which are these interpretations, are called interpretations of F and M, F and R in M, and they are called just relations and operations. And constants, just interpretations of constant symbols in a structure are just called constants. So now what we can do, we can interpret a term over a language L in an L structure as some function which takes variables and kind of, if we substitute things for the variables, evaluates that and gives us an element of the structure. So say we have an L structure M and the term T over the language L. Now we can define this interpretation of T, which is a function. It takes in V things, or the cardinality of V things for the variables to substitute in, which are all going to be elements of M, where V is the set of all variables that occur in T. And then this gives us an element of M. We kind of evaluate the term when substituting in all these things for the variables that occur in the term. And this is also defined recursively. If we have something to substitute in for the variables, say x dash, then for constant symbol C, we define the interpretation of C evaluated at this x to be just the constant. So, I mean, the unique element that the constant specifies. If we have that the term is the ith variable, just as a variable, because remember, terms could also just be variables. A term can be 1 times x, but it can also just be x. So if the term is ai, for ai just a variable which occurs in T, the ith variable, note we ordered the variables implicitly, strictly speaking, well ordered them, doesn't really matter. But yeah, so if this term is ai for I, the ith variable which occurs in T, we say that the interpretation of ai evaluated at x is going to be xi. And lastly, but not leastly, this is probably the most important point, is that when we have n terms, an n-ary function symbol, operation symbol, and we interpret f of t1 through tn and evaluate it at x, we get the same thing as when we interpret f and then evaluate it at all the terms, interpreted and evaluated at x. So maybe let me just stop quickly. I've been going pretty fast because these are just most definitions. They have to say that the whole talk is basically going to be definitions. But still, maybe it's good to check in. Does anybody have any questions? Is everything clear so far? All right. All right. So let me repeat it. Right. So let me repeat it for recording because people watching the recording can't hear what people in the Discord are saying. So I've been asked what like the key points to take away from the definition so far. So basically what we've been doing, we've been just defining a sort of background in which we can formalize some axiomatic systems and things like that in set theory, by which is called modal theory. And these 3 points, you don't really have to memorize them whatsoever. It's going to be pretty intuitive how to interpret terms. Like say we have the term 1 times x in the language, that was the example. And say we have now a structure, the real numbers with multiplication. So for a structure we specify a set, the operations, the relations, the constants. I mean, the constants also operations, but let me just add it in as well. And so we have this language, one constant 1, and multiplication, which is a binary operation symbol. Now, a structure for this language would be the real numbers with 1, the constant, interpreted as the real number 1, or the constant function from the singleton empty set to that, but yeah, the real number 1 basically, and multiplication interpreted as the binary operation on the real numbers, which actually multiplies numbers. Then we have that, we have this term 1 times x over the language, and we can interpret that in this structure as a function which takes in one input for the variable x and gives one output, which, for example, would take in 2 and give 1 times 2 as an output. So the interpretation of 1 times x over the structure of the real numbers on the multiplication and 1 is 1 would give us x as the output when we input x. So basically, it's going to be way more clear what's going on once we see some examples. So far, it's just kind of building up the background we can walk over to kind of formalize things. So let's continue, and there's going to be one more slide where we recursively define something, and then there's going to be more sensible things, less technical ones. So we've defined interpretations of terms, but now we can define interpretations of formulae, and in particular interpretations of sentences in structures. So now when we have some statement in a language, we can look at a structure over the language and see whether the statement holds in the structure or it doesn't. And we do this as following. We define this as following. When we have a formula over the language L and the structure M, as well some x dash to substitute in for the variables, we in the formula phi, we say that the structure models the formula evaluated at that x, and those things to substitute in for the variables. Whenever we can recursively show so, and recursively we show it as the following. First of all, if the formula is the equality of two terms, then we're going to say the structure models the formula evaluated at x whenever the terms evaluated at x interpreted the structure equate, right? So say p is 1 times x and q is x, those are two terms over the language from our example, then the real numbers in the multiplication as the multiplication thingy and multiplication symbol and 1 as the one constant indeed models that 1 times x equals x, which is a formula in one free variable over the language. So second of all, if you have a relation, n-ary relation symbol r and n terms, we say that the structure models now this formula evaluated at some x, if and only if the interpreted relation applies to the interpreted terms at x. So maybe say our language would consist of a binary relation symbol less than, and we have two terms a and b, then the structure models that the string a less than b is true, say the terms have no variables, and then we don't have to substitute anything in for x. Then this would hold precisely when the interpretation of a is less than the interpretation of b, when less than is also interpreted in the structure. So the third point is that if the formula is negation, then the structure models the formula precisely when it doesn't model what is the negation of, which is also kind of self-evident. Again, everything evaluated at x when we substitute into things. And fourth point is the same thing for conjunction. And the fifth point is for quantification, that when the formula is that there exists some v such that psi, and actually, I probably should add in some more parentheses there, but it doesn't really matter, it's kind of just technicalities. Just there exists some v such that psi, then the structure is going to model this when we can find some w, an element of M, such that psi holds at x and w. So we kind of what we're doing here, we're taking out all these logical symbols out of the formalities of how we build strings to be terms and formula and sentences, and actually interpreting them in terms of like real maths and set theory. And so when we have a sentence phi, then we have nothing to substitute in for x. I mean, there are no variables to substitute things for, so we just write that M models phi instead of M models the phi of empty set. And we say that M is then a model of phi. Right, so I recall again a theory is just a set of sentences of a language, and I would say that a model of a theory is a structure which models all of the axioms, all of the elements of the theory, all of the sentences in the theory. And again, theory is also called axiomatic system. Maybe that clears a little bit up what's going on. And now we're going to have some examples I think that might help. So the first example, a language needs to have operation symbols, constants, but relation symbols, well, none of them. I mean, it needs to have specified amounts of all of them and have symbols dedicated to all the things specified. So we can consider the language with one binary relation symbol, this tilde, and now we can have form these two sentences. The first sentence is for all x, it's not true that x is related to x, so tilde is going to be a binary relation symbol. And the second sentence is that for all x and for all y, this implication holds that tilde is symmetric, basically. And now this is a theory, this is kind of an axiomatic systems, and these would be our two axioms, and the only symbol that we use is this binary relation symbol. And now models of this theory correspond to simple undirected graphs, right? We can think of this relation, binary relation, to be interpreted as adjacency, and then the elements of a structure will be the vertices of an undirected simple graph. Someone might call it the theory of graphs or something like that. Now, here's another example, maybe a more important one. It's piano arithmetic. It can be viewed as an axiomatic system, so a set of sentences over a language which has the two binary operation symbols plus and times, a unary operation symbol successor, and the constant symbol 0. And now we can formulate piano arithmetic as the following set of sentences. So the following, given by the following axioms. We have the first axiom is that for every x, the successor of x is not 0, and then for all x, for all y, that s of x is s of y. Oh, parentheses missing, my bad. Got to fix it later. So here there should be closing parentheses. This implies x equals y, and then so on and so on. We see just the axioms of piano arithmetic. If you put them in a set, and we consider them all as strings in this language, we've now created something which kind of is a formalization of what piano arithmetic is. And also notice I write union J. Now, strictly speaking, piano arithmetic is going to have infinitely many axioms because of induction. Because induction is something that's really a second order thing, if you're familiar with something like that, we need to add an axiom for every formula saying that it satisfies induction, and this is called induction schema, and this J is a set containing a sentence for every formula saying that it satisfies induction. So as you see, the whole point of this section is just to see that we have languages over which we can form strings which represent mathematical statements and terms and formulae, and then we can interpret them in structures, in models of them. This is actually a very fundamental way of viewing mathematics. And it's very useful in universal algebra because universal algebra is going to take this view of algebraic structures. So now, what is an algebraic structure? Well, an algebraic structure is simply a structure of a language no relation symbols. So maybe we can take an example of, say, groups. We can take the language which contains a binary operation symbol star, a unary operation symbol inversion, and a constant symbol 1. And then we can say that the theory of groups is the following, which state associativity of this binary operation symbol star, that 1 is a neutral element, and that inversion is actually, well, it satisfies the obvious properties. And we get the theory of groups, and now models of this theory are going to be groups, basically. And one remark is just a notation that often instead of writing, so as a footnote in one of the first slides, I remarked that formally a language we can consider as one, a structure we consider as one object as like a triple, we can consider to be written as this. So then a group is an ordered quadruple here, g times -1, 1, instead of this over kind of triple. But that's just a formality. Right, so let's continue. Now we've defined all the model theoretic basics. Now we can move on to more universal algebraic things. Though I guess first we also have to consider homomorphisms of structures. And homomorphisms of structures are going to be the notion of morphism, so it's going to be viewable through category theory, though that's usually not done very much, it's just done without categories, but you can also do it with categories. You can consider what's called Lavoisier theories, and then you can interpret things like group objects to a more generality, to consider like just algebraic structure objects. But it's getting tangential. Back to homomorphisms. Homomorphisms between two L structures, M and N, is just a function satisfying that we can kind of switch around the order if we first do the function and then some operation G, or the other way around. And the same thing for relations, except now we have this application that if we have a relation between x1 through xn in M, if M is the domain of the homomorphism, then this implies the relation holding in the codomain. And so this now defines what a homomorphism of structures is. And if we restrict our view to just algebraic structures, then the second condition is irrelevant because there are no relation symbols. And so the only condition for homomorphisms between algebraic structures is going to be that, again, we can first apply operations, then the function, or the way around. And so, one small remark, because of the way we define constants as operations, it's good to note that indeed we want that the homomorphism applied to a constant symbol is going to be the interpretation of the constant symbol respectively in the other structure. And here's a small lemma. It's that, well, first of all, now we have the data of morphisms. Now we can make structures of our language into a category. And now we can speak of isomorphisms, monomorphisms, etc. And one good thing to know is what isomorphisms of structures are. And isomorphisms of structures are precisely bijective homomorphisms such that the implication in the second point can be reversed. But if you consider algebraic structures, then the second point is completely irrelevant. There are no relation symbols. And so it suffices to say that isomorphisms are bijective homomorphisms when considering algebraic structures. Right. So also we have now a category. We can also consider things like products and coproducts and equalizers and kernels and things like that. And that's useful. So let's move on. Another very natural notion is now of substructures. And now I specialize the algebraic structures because that's what's relevant in universal algebra. But we can also do substructures and things like that with more general structures. So a substructure of another structure M, let's say a substructure N of a structure M, is going to be just a structure whose underlying set is a subset of M. So this is all happening over the same language, to be sure, such that the operation symbols restrict properly. And now here's a lemma that we can characterize products in this category just the obvious way by taking the Cartesian product of, so when we take a product of structures, we just can take the Cartesian product of the underlying sets and then define all the interpretations of the operations in the product to be component-wise. So this might look a little bit messy with the indices, but really what we're doing, we're just multiplying component-wise, not multiplying, but applying the operation f component-wise. So you can check that this defines the product. So now we can continue on to talk about congruences. And one thing that you can often do in algebraic structures, you can take quotients. You can take quotients of groups, you can take quotients of rings or modules, you can take quotients of loops, etc. And we can generalize this in universal algebra, but with one restrictions. Usually, maybe what you see in more classical algebra is that you quotient by a subgroup or a substructure. In general terms, you quotient by an equivalence relation, just with sets, and just, in general, you quotient by equivalence relations. And when you quotient, say, a group by a normal subgroup, really what you're doing, you're quotienting the group by an equivalence relation that's induced by that normal subgroup. And so when we now look at it in generality, we have to consider when we quotient an algebraic structure by a certain kind of equivalence relation. And this certain kind of equivalence relation is called a congruence. So a congruence in an algebraic structure is an equivalence relation which also is a substructure of the direct product of the structure with itself when constructed as in the previous slide. So now when we have a congruence, we can form a quotient structure. We take the quotient set and then we define the operations just the obvious way by taking the elements out of the equivalence, the representatives of equivalence classes out of the equivalence classes, applying the operation in the structure, and then taking the equivalence class. And one can check this is well defined, and this works out. In fact, here, just as an example proof, so you might know I'm not really giving many proofs here, because they're all pretty straightforward, or at least so far. Later there'll be large results, which will be very difficult to prove and not so straightforward, but that's another issue. But the reason I'm not really giving proofs so far is because they're all very straightforward, and you can check them as exercises if you wish. And generally, this talk is really technical. It's more preparation for the talk next week. But yes, let's check that quotient structures are defined well. So it suffices to check that when we choose different representatives of the inputs, we get the same output. So say we have the representative A1, A1 prime, AN and AM prime, and so on, everything in between. And I think this should say C times C. Oh no, it's correct. It's in C because C is the congruence in translation. So all this says is, suppose A1 is the equivalence class of A1 is the equivalence class of A1 prime. Suppose the equivalence class of A2 is the equivalence class of A2 prime, etc., and the equivalence class of A and the equivalence class of AN prime. Um, and since now the congruence is a substructure of M times M, which was a condition we required for the equivalence relation to satisfy, we now know that when we apply an operation, it remains in the substructure. So now, hence by the construction of the direct product, we have that if we evaluate this component-wise, we get that f of a1 through an has the same equivalence class as f of a1 prime through an prime. And so we get the same equivalence class out, and so this function, this operation, as interpreted, is well defined. And this indeed gives us the desired structure. So maybe let's take an example, though this may be a kind of general example of what's going on. For any group, when we have a normal subgroup, we can find the congruence such that the quotient by the normal subgroup is the same thing as the quotient by the congruence by considering this equivalence relation. You can check this indeed is a substructure of G times G, a subgroup of G times G. And so this indeed defines a congruence. And similarly for any congruence, it's going to be an equivalence relation that we can quotient by. We can take the equivalence class of the neutral element of the group, and this is going to be normal subgroup. And so we get a bijective, strictly speaking, inclusion reversion correspondence between normal subgroups and congruences on a group. And that this inclusion reversing is something that I might remark on is that important in universal algebra. Often in universal algebra, you want to consider order theoretic properties of substructures. And then you get things which are called lattices, and you can study a lot of things with lattice theory. And I didn't go into it here, but maybe we'll see it a little bit more in the latter talk next week. But yeah, universal algebra is very often important to look at order theoretic things. And so here, the remark is inclusion reversing is actually important for certain things. Right, let's continue. So now, say we have two algebraic structures, again over the same language, and some homomorphisms, one homomorphism, then we can define its kernel. And similarly to how instead of quotienting by substructures, we quotient by equivalence relations, now the kernel is not a substructure, it's an equivalence relation. It's going to be in fact a congruence. It's going to be the following congruence. It's going to be the equalizer of f and f in the category of sets. It's going to be all the points x, y, and m times m, so just fx is f of y. So you can check this as a substructure of the direct product of m and m, and so we get the congruence in fact. You can also check that. So now this in fact, as say groups or modules, completely characterizes congruences. A congruence is just a kernel of a thing, of a homomorphism. You can check that every congruence is the kernel of a homomorphism, namely of the quotient map, and every homomorphism is the kernel. It's not a kernel, but the kernel of any homomorphism is a congruence. This is in fact a bijective correspondence. So it's kind of characterizes congruences. Now we can state, for example, the general statement of the first isomorphism theorem. You can also state an analogous statement for the second isomorphism theorem. I'm not sure about the third one, but here I'll just state the first one. So first of all, when you have a homomorphism between two structures, the image within the algebraic structure, the image is going to be a substructure of the codomain of the homomorphism, and it's going to be in fact isomorphic to the quotient of the domain by this congruence of the kernel of f. And you can check this just by the map as you do with groups or modules, just a little bit of diagram chasing. So this is already kind of convenient. Now that we've defined algebraic structures in this great generality, we can immediately, whenever we have the context of some algebraic structure, have the first isomorphism theorem just granted to us because we've already proven it in the great generality. So now we define some of the more basic notions of universal algebra, and that's not really what universal algebra is about. The universal algebra studies phenomena at a larger scale, namely with varieties, which are certain kinds of classes. So let's define a variety, but first I'll define what an equational class is, because variety is going to be a special case of an equational class. So an equational class over a language is just the set or the class of all models of a given theory. So a class is equational if the elements of the class are models of some theory over some language. And so a variety is just, so maybe what's the point of studying equational classes? Well, they're pretty intuitive objects, as the name says. Equational classes are classes which are given by equations. So we're kind of studying the equations by studying the classes which arise out of them in some sense. Um, but now when we can do this in universal algebra, we get what's called varieties. So a variety is an equational class over a language with no relation symbols. So over a language that gives algebraic structures. Um, and this can also be characterized alternatively. Actually, I think this wasn't the original definition. Um, oh, well, you'll see the original definition later. But for now, then, let's maybe look at an example. Um, if you have any equational class of algebraic structures, it's going to be a variety. So it suffices to just look at the theory of a language without relation symbols, say the theory of groups. And now the classical models of the theory of groups, so just the classical groups, is going to be a variety. Similarly, the classical rings is a variety, the classical monoids is a variety, and so on. And really, universal algebra is about studying varieties, about studying properties of the algebraic structures in varieties by studying just general things about the varieties. That's basically the main object you study in universal algebra. So now, here's just something convenient to have. It's that an image of an algebraic structure in a homomorphism is called the homomorphic image, kind of a tautological name as always. And it's a substructure, as noted in the first isomorphism theorem. And so here's, I think, the original definition of an algebraic structure, sorry, of a variety. So a class of algebraic structure is equational, so it's a variety precisely when it's closed under products, homomorphic images, and substructures. So you can check that these two definitions are equivalent. It's a little bit tricky to do, but with a tiny bit of machinery, you can do this pretty well. So that's another characterization of varieties. It's useful. So now, immediate corollary, if you have that the product of some two elements of a class that are algebraic structures isn't in the class cannot be a variety. And we might note that, say, the product of the real numbers with the real numbers when viewed as, say, rings is not a field. However, the real numbers are a field, so fields cannot form a variety. They are not closed under products. So that's already one example of something that's not a variety. And you might ask, well, fields are kind of defined by equations. Why do they not form a variety? Well, the reason they do not form a variety is because we kind of awkwardly circle out 0 not to have a multiplicative inverse, because that's kind of impossible. And it just makes things very tricky when you circle out one element from having a multiplicative inverse. It just makes things kind of broken. Alright, so now a quick exercise now maybe to prove that varieties are close on the formations of quotients by congruences. You can just do this by noting that they're close on the homomorphic images and thinking about quotient maps. But that's a thing to think about maybe. So now, one very important theorem in universal algebra is due to Birkhoff, and it has to do with these class operations. I mean, we have a class of algebraic structures about the same language. So always when I say algebraic structures in the talk, they're always about the same language, when they're like in the same slide, in the same bubble here. So if you have a class C of algebraic structures, we have these three classes associated, H of C, P of C, and S of C, and they're just the classes of homomorphic images, products, and substructures of algebraic structures from C. So it's pretty straightforward, but now we have this characterization of varieties, or maybe of varieties generated by a class, the smallest variety containing a class, or the intersection of all varieties containing a class. Namely, if you have a class C of algebraic structures, the smallest variety containing C is this thing. We first close C under products, then under subalgebras, or subalgebraic structures, and then under homomorphic images. And this is then the variety generated by C. So this finishes up the greatest part of the talk. It's just basically the universal algebra definitions that we'll need next week. Then we can look at some fun theorems for the last couple slides. So let's start off with some fun theorems in model theory. So a theory of a language, now any language that can have relation symbols doesn't need to be a theory of algebraic structures. It's called satisfiable if it has a model, right? For example, we can take the theory for all x, not x equals x in any language. We don't really need any symbols there. And it's not going to be satisfiable, because when we interpret it, it just won't work, because there will be x. Oh, actually, it will be satisfiable, because it will have the empty structure satisfies it, but if you add the existent x, it won't be satisfiable. Like a second sentence, the exist x such that x equals x, and for all x, x equals x is false. These two sentences, when put into a theory, they are not satisfiable because they exist in a model. It's impossible to have something which behaves according to those axioms in said theory. Um, so now we have a nice theorem that a theory is satisfiable if every finite subtheory is satisfiable. This is called compactness, and it's a very important theory, model theorem. It's just good to know. So now, this is not quite a theorem, but this is just a neat concept to know, namely this the concept of definability. If you have an L structure M for some language L, then a subset of the underlying set of this structure is called definable if it's given by all elements satisfying certain formula in one free variable. Um, and that's just something you need to note. And now we can have theorems like integers aren't definable into reals when Newton addition as like into language plus minus 0, things like that. And this kind of can express formally a lot of intuitive things that in some sense we cannot define the integers through addition, subtraction, and 0 when we start with real numbers. Um, so that's just something very neat of a concept. So now the last theorem I note here is the theorem of Löwenheim's column. So if you have a first order logic theory with an infinite model, then it has an infinite model of every cardinality, transfinite cardinality. And here it's important to note that we're working with first order logic, and in other logics, when we replace the way we build sentences, this doesn't necessarily work. Well, in first order logic, it's impossible to have a theory which has a unique isomorphism model of some infinite cardinality. So immediate corollary, Peano arithmetics has non-standard models. This follows because it has an infinite model, I mean the natural numbers, and so it has a model of every cardinality, and in particular has models which are different from the standard model. So of course, by the standard model, I just mean the natural numbers and addition, successive multiplication, and 0. And now let's see some type theorems in US algebra, actually just one theorem. So say we have, so first we need to have some definitions that we'll also need next talk, but they're also present the theorem here. If you have two relations on a set, the relational product is just this thing, which is kind of a generalization of backwards composition. Sometimes the relational product is just defined a little bit differently. It just depends on convention. But it's basically generalizing composition of functions to arbitrary relations, and it's defined the following. And now we have an algebraic structure congruence permutable if congruences permute under the relational product to be commutative, and the variety is called congruence permutable if each of its elements is congruence permutable. And that congruences permute under so that we can form relational products of congruences just makes sense because congruences are binary relations on the underlying set of the algebraic structure. And now we have a nice characterization of congruence permutable varieties, and this is actually very in the spirit of general theorems in universal algebra. So most theorems in universal algebra look like this. We characterize some property of a variety by the existence of certain terms in the language being satisfied in a particular way by element of the variety. So the theorem, so these terms are going to be called Malchev terms, this P, and the variety V is going to be congruence permutable precisely when there exists a term P in the underlying language with free variables, such that for any structure in V, we have that the structure models that P of X, Y, and Y is X, and the structure models that P of X, X, and Y is Y. So that's maybe just, I mean, this isn't intuitive for anybody who hasn't seen anything about congruence permutability and things like that, but the reason I put the theorem here is because it illustrates very well the sort of general things we're going for in universal algebra. We're studying these large objects varieties by kind of considering the terms we can find into structures to satisfy certain equations. And then we get some larger phenomena, larger properties of the varieties like congruence permutability. So this actually finishes up my talk. Maybe it's quite fast and short, and maybe here just a little bit of further reading. For anybody interested, everything that I presented can be found in these two books, both GTM books. The first one by David Marker, Model Theory Introduction. The second one by Stanley Burris and H.B. Sankapanaba, sorry if I pronounced that wrong, Course in Universal Algebra, actually. These are the main books where I learned this stuff from. So maybe, does anybody have any questions? Right. So an n-ary operation. So usually when you think of an operation, it's a binary operation. So let me find the appropriate slide. Actually, I'm not sure what slide would be most appropriate. Let's just go with this one. So yeah. So but the difference is that a binary operation is an operation which kind of takes in two inputs. So it's a function from a set times itself to the set. Um, but an n-ary operation is a function which takes in n inputs from a set and outputs the same element, um, outputs an element from the set as well. Um, so that's the difference. And an n-ary operation is just a binary. It's like a binary operation, but you take n inputs instead of just two, right? It's like instead of addition, you can have something which takes three inputs. And this allows us to consider algebraic structures where the operation is taking more inputs. It's pretty straightforward in that sense. Um, so I hope that answers the question. Or is it still not quite clear? Or? Well, because this way we consider quite a large more. So actually, let me repeat it for recording. So the question is, why do we consider n-ary operations in general rather than just binary operations? And now the reason we do this is because in universal algebra, this allows us to consider a vast majority more of structures. We don't have to restrict ourselves this way. The theorems still work, and in fact, it gives us a richer structure of varieties to investigate. For example, if we go back to the piano arithmetics theory, we can consider it in universal algebra because there are no relation symbols, right? And so theorems in universal algebra hold true about piano arithmetic. But we can only do this because there's a unary operation symbol successor, right? And we have constants as well, which are nuller operation symbols. And these all are very important things to have, and it's just useful to have them. Maybe one structure you might want to look at is heaps, and heaps actually have a ternary, which means arity-free operation in them, and we can also consider them universal algebra. It's just interesting to have theorems about them. Um, yeah, so I hope that answers the question. What the point of yeah. All right. Any other questions? All right. So if there are no other questions, the talk is over. Uh, if anybody wasn't there for the beginning or there's a recording, there will be a recording. Let's see.